To speak here. So this is joint work with Ewan Davies and Juspreet Singh Sandhu from Colorado State and Jonathan Shi. Okay, so I'll get right to the problem, the Sherrington-Kirkpatrick model. So this is a model from statistical physics giving a random distribution on particles that can take one of two spins. Okay, in statistical physics, we often care about particles with some kind of geometry. So maybe they're on a lattice with some nearest neighbor interactions. It turns out it's much easier to consider a mean field model where every particle interacts with everyone else. Okay, and the Sherrington-Kirkpatrick model is an Ising model. So that means there's pairwise interactions between particles. Okay, and then we presume that this interaction matrix A is a Gaussian random matrix. Okay, so all the off-diagonal entries are normally distributed with variance 1 over n, and we assume A is symmetric. Okay, so it turns out these mean field models are much easier to study and exhibit many of the behaviors we expect from statistical physics. Okay, so then our problem is the sampling problem. So we want to sample from this distribution with negligible total variation distance. Okay, and then importantly, there's this inverse temperature parameter beta here. And it's conjectured that we can do this sampling efficiently in the high temperature regime. Okay, and the relevant kind of transition point here is beta equals 1. Okay, so this conjecture made informally by physicists and then more formally here is that in the high temperature, also called this replica-symmetric regime, where beta is less than 1, with high probability over A, there's an efficient, i.e. polynomial-time sampling algorithm. A stronger form of this conjecture would say that actually the simplest, the canonical algorithm of Glauber dynamics works, i.e. it has rapid mixing. Okay, so why do we care about this model? What's the big picture? This is a case of wanting average case sampling from some random distribution. It turns out there's kind of relatively few results, I think, for sampling from random distributions, and this is kind of, in some sense, one of the simplest unsolved problems here. Okay, there's lots of implications for Bayesian inference because in posterior distributions themselves are random because they were determined by random data. Okay, and you can, for instance, make direct connections between this and sampling from the posterior for a spiked Wigner model, among others. Okay, the distributions. This is a distribution on the hypercube. It has different challenges from continuous distributions like those on the sphere. And then relevant for us, this proof. The proofs use analysis of diffusion models and related ideas that we'll see. Okay, so let's jump into it. So I'll talk about first our first algorithm for sampling from the SK model, and then kind of a different, more simplified one. Okay, so here's the landscape. Okay, so for the SK model, we know there's this phase transition at beta equals 1 in terms of a lot of properties about the distribution change between this high and low temperature regimes. Okay, relevant for us is the problem of sampling. So it's conjectured that it should be easy to sample at high temperature, so beta less than 1, and hard to sample in polynomial time above this threshold. Okay, and there's been a lot of work on this problem, a lot by some of the participants in this workshop. Okay, so I'll kind of divide between two different kinds of guarantees that people have gotten. Okay, so first, kind of the strong sampling guarantees about negligible total variation distance. This was previously known up to 0.295 by Nima Nari, Fred Kohler, and Jun Wang. And then our work kind of stretches this region up to beta equals 1/2. Okay, on the side of weaker guarantees, so there's this work by Ahmed El-Louis, Andrea Montanari, and Mark Selke, which gets a algorithm using algorithmic stochastic localization that gets non-trivial Wasserstein distance, that's little o of n in Wasserstein W2 squared, okay? And then later on, Celentano kind of as a result made this method work up to the threshold of beta equals 1, okay? And on the side of hardness, okay, so it's conjecture this is hard above beta equals 1. And then in this same paper, Ahmed and collaborators showed that this is hard for stable algorithms, algorithms that are stable to perturbations in A as evidence of hardness. Okay, so just this table again, and then I also note that there's similar work on the spherical p-spin model. So this is over the sphere, and then Bryce Huang will talk about this story tomorrow. Okay, so there's two main approaches here. So stochastic localization and algorithmic stochastic localization. Very related. So stochastic localization, you can use it to prove functional inequalities. So this gives you strong results. What functional inequalities tells you is that you get mixing for the natural Markov chain. So for example, Glauber dynamics. Okay, but it requires some strong conditions to work. And then there's also algorithmic stochastic localization, which gives weaker results in the sense that it's saying like there exists some other algorithm that works and typically requires weaker conditions. Okay, so stochastic localization is really diffusion models by another name. Okay, so there's a kind of a difference of perspective, except there's kind of a difference of perspective. So in machine learning, when you talk about diffusion models, we often think about we're learning some distribution from data. So samples drawn from this unknown distribution, and you learn the score function to simulate this process. So this stochastic localization is independently proposed in probability theory. And the way it's often used is you're given some known distribution, mu, and you either want to sample from it or prove some kind of structural properties. And using this kind of same process, you want to approximate or understand the score function to do that. Okay, so for this SK model, previous work with stochastic localization gave these functional inequalities, these negligible TV distance guarantees. One kind of shortcoming of these is they previously used kind of, in some sense, a worst case analysis that you rely on spectral properties of your matrix A, and where there's kind of a lot more information maybe from the spin glass theory that you're not using. And then algorithmic stochastic localization gets up to beta equals 1, but gives you this weaker guarantee. Okay, and then similar story for the spherical p-spin. So there's kind of other separate techniques that are used in the spherical p-spin. It's kind of challenging to try and apply them here. So we have some different methods. Okay, so I'll go right to our main results now. Okay, so we're in the beta less than 1/2 regime. Okay, so given any fixed delta with probably 1 minus delta over A, we have an efficient algorithm that's based on approximate stochastic localization and a rejection sampling with Jarzynski's equality that gives a sample that's has negligible TV distance from the Gibbs distribution. And more precisely, we get epsilon error in time that scales as exponential in 1 over epsilon, or 1 over log n error in polynomial time. Okay, and then we can, and then our second work, we bootstrap this to a weak functional inequality, a weak Poincaré inequality. So I'll describe what that means. But what that means algorithmically is you can do a simpler algorithm, which is after you get a warm start, just run Glauber dynamics. Okay, and this kind of progression of first doing ASL and then getting a functional inequality also mirrors this story for spherical p-spin that Bryce can tell us about tomorrow. Okay, and then of course I can advertise this as an algorithm based on diffusion models. Okay, so let's talk about diffusion models and stochastic localization. So stochastic localization you can think of as a reparameterization of diffusion models. Okay, so for convenience, we'll just consider distributions that are defined on the hypercube. Okay, we know the usual variance exploding diffusion model is you simply add Gaussian noise, i.e. Brownian motion. Okay, now, stochastic localization is a different parameterization, rescaling, so that yt equals t times x at time 1 over t, and knowing this Brownian motion for like this with this inverse time is also Brownian motion. You can get an expression for what this yt looks like. Okay, so this process is you can think about you have some x0 drawn from your distribution mu. Okay, and you scale it by t, and then you add this Gaussian noise. Okay, and as t increases now, the signal to noise ratio between your x0 and your Gaussian noise is square root t, so it goes to infinity. So maybe just to draw it so you have a picture. So we start at this time goes kind of oppositely from the time for diffusion models that you might be familiar with. So at time 0, we start out with just y0 equals 0. Okay, and as time goes on, we kind of have the signal is stronger and stronger, so kind of separate out like this. Okay, and then this will be yt, so I'll call this pt, the stochastic localization distribution at time t. Okay, and then this is kind of opposite from the maybe the forward diffusion model parameterization, which goes in the opposite direction and it is rescaled. Okay, so the difference here is like the signal is getting stronger and stronger. So as time goes on, you're going to infinity in the direction of the signal. Okay. Okay, so you can write down SD for this. Okay, this is you can just take the reverse SD for diffusion models and use this reparameterization. You find that the drift, it's very convenient because the drift term is exactly this, this posterior mean. Okay, so given your observation yt, this posterior distribution is what is the distribution of x0 conditioned on this observation. Okay, and this drift is the mean of that distribution. And moreover, this posterior distribution has an extremely nice form that with this parameterization is simply the original distribution tilted by your yt. Okay, this makes sense. The signal strength is getting stronger and stronger, and the posterior distribution is just your distribution tilted in that direction. Okay, so the kind of localization perspective is more to think about this posterior distribution. Okay, so you can always sample by running it for some time t. Okay, you have your sample yt. This induces some posterior distribution on your hypercube that's kind of more concentrated towards the signal, right? So you can then draw some sigma from this posterior distribution, which is your distribution tilted by yt. Okay, and then that will give you a sample from you. Okay, so and then kind of you can formalize this saying, okay, this posterior is a measured value martingale that converges to a delta distribution where the point is drawn from your original distribution. Okay, so if we want to make this algorithmic, okay, so this currently relies on knowing what this mean is, okay, but you could also make this computational by using some kind of algorithmic estimate of it, and we'll call that approximate stochastic localization, or algorithmic stochastic localization. Okay. Okay, so where might we get this m hat? Okay, this is from the, we can get this from the TAP equation. This is by Tallis, Anderson, and Palmer. This is a physics prediction that has later on been made more rigorous. Okay, so what this says is they give this, there's this expression called this tap free energy, and its minimum gives an approximation of the free energy of the system. Okay, so here's a more general Gibbs distribution where we also have this tilt y, okay, and then z here is the partition function or a normalizing constant for this distribution. Okay, so we know that if we differentiate log z, we can get the, in terms of this tilt, we can get the mean and covariance of the distribution. Okay, so that's how you, that's how you can get an estimate for this mean and covariance. Okay, and this tap equation will give you kind of a proximate relation between this tilt and the mean. You can also differentiate it to get a approximate relation between the mean and the covariance. Okay, there's some rigorous results here. A challenge for us, though, is that there's some complicated dependence between y and a because y is drawn from the stochastic localization process.
So presumably this approximation becomes better and better for small detail.
So yeah. So and in particular, you should need beta less than y. You should be in the high temperature regime. Okay. So the details of this equation will not matter for us. I just want to show you how you could write it down. So for beta less than 1/2, things are particularly nice because the tap free energy is convex. Okay, so we know it has a strictly convex, and we know it has a unique minimizer. You can solve it by setting the gradient equals 0. Okay, when you take the derivative and get this mean, the estimate it gives you is exactly this this minimizer. Okay, so we'll call this m hat of y. Okay, so this is what we would want to plug into to our approximate stochastic localization. Okay, and you can also take another derivative, and I call this Hessian q hat inverse. Okay, so it turns out then this will q hat will be estimate of the covariance of the tilted distribution that has this mean m. Okay.
So the
yeah.
transition, so for under a half it's convex, and what's the transition is 1 or a half?
The transition is 1. So after that, it should be like locally convex, but not globally, and that creates some difficulties for. So that's why we only have so far pushed to 1/2. Yeah.
So your analysis kind of needed to be globally convex.
Yeah. So this is a similar abstraction to the original ASL paper. Also went to beta equals 1/2, and then later on Michael Salentano.
I think it's still globally convex. We just don't know how to prove it.
Okay. Okay.
It should be globally convex up to beta equals 1. We don't know how to prove it. Up to beta equals 1/2, it's very easy to show.
Okay. Okay, so let's take a look at what's the process we're trying to simulate. So the ideal process is this stochastic localization process with the true mean. So it's helpful also to write down what the evolution of the mean is. Okay, so because this stochastic localization process is a martingale, if you write down the SD for the mean, it has no drifter, and it's just this covariance times dVt. Okay, so we'll call this the second equation Hessian dynamics, okay? Because Q is kind of related to the Hessian of the tap free energy. Okay, so our primary algorithm will be you take the algorithmic version of this, so you have a m hat instead. Now we want our m hat to solve the tap equation. Okay, so rather than kind of solve the tap equation for every value of y, we can just take the tap equation, kind of differentiate it in t, and just enforce that it stays satisfied for all time. Okay, so if you do that, you directly get an SDE on m hat. Okay, there is another option you could do, which is instead of trying to match, note that when we try to match the SL part, right, the equation on m hat becomes a little unruly. We could also try to do the opposite, where we match the Hessian dynamics part, and now it's the kind of equation on tilt that becomes a little unruly. Okay, so this is an alternative that PhD does call this potential Hessian dynamics. And this is a high temperature version of potential Hessian ascent for optimization. So this previously analyzed by some of my co-authors. Okay, and this turns out to be kind of very although I'm going to say results about the running ASL top, it turns out that it's very useful to kind of compare to this process in the proof.
Again, why do you have this, in the ideal process, you have the red one? I mean, if you knew M, you could have run the blue one, right? Just run the stochastic localization.
Yeah, so M is a function of Y. But it's kind of nice to kind of close the equation and say, oh, let's also give the equation for how M evolves. In particular, when you're trying to make an algorithmic version of this, there's kind of it shows that there's kind of two possibilities that you could do. You could match either one of these equations. You can't match them both at the same time if you use the approximate M hat. Yeah.
And in your problem setup, are you assuming access to A? Or
Yes, you absolutely have access to A. Yes. Yeah. Okay. So a key quantity we want is to bound this the error between the drift term, which is the error between the estimated mean and the actual mean. Okay, and then so in this first paper on algorithmic stochastic localization, so Ahmed and his co-authors show you can get a little O of n error, and that gets you the Wasserstein error. Okay, so it turns out that this mean estimate is kind of difficult to analyze directly. The covariance estimate Q hat is easier to analyze, and then Ahmed also had a paper where getting covariance error bounds in the case where you don't have a tilt, okay? So our strategy is to try and extend this to the case where we have this tilt given by ASL, so to get this Frobenius norm error for our estimate Q hat. One nuance is that this expectation is under this this should be the SL, not the ASL. The SL process, which is kind of complex, but there's it's contiguous to the simpler planted model, so you can analyze it there. Okay, and then once you have this covariance estimate, the idea is to kind of integrate it with Grandwall with some additional properties to get back this mean estimate. Okay, and then once you have this mean estimate being constant, okay, then the standard algorithm, since this is a drift for two SDEs, right? Then by the standard Gersonov argument, you can get for constant time that the KL divergence between these is order 1. Okay, so now we want to reduce to negligible TV distance. How do we do that? A very natural idea. So if you have distributions, if you add a distribution that's big O of 1 close, you can try to do rejection sampling. Okay, so this immediately has a problem. Rejection sampling requires knowing the density of the proposal distribution. Okay, but our proposal distribution was just implicitly defined by this SDE that we followed. Okay. So the solution is to actually find another explicitly defined distribution, rho t, and then first correct to that by Jarzynski's equality. Okay, and then you can do the rejection sampling. Another thing to note is you can only run, to keep this order 1, you can only run ASL for constant time. Okay, so after constant time, you have to directly sample from the localized or this posterior distribution, and you can we do that by showing a functional inequality for that. So that's you can directly sample from that with a Markov chain. Okay, so what's Jarzynski's equality? This is a method. You can derive it from Feynman-Kautz formula, either for sampling or computing normalizing constants for some target distribution given some kind of arbitrary annealing sequence. Okay, and there's freedom for you to choose what this annealing sequence is and a drift term. Okay, and you know that the distribution you'll follow, or if you run your SDE, you won't match rho t in general. Okay, and Jarzynski equality gives you the correction weights you need, or for importance, the importance weights you need so that it will match the distribution rho t. Okay, which is the exponential of these WTs. Of course, this is not free because in general, the problem with this importance sampling is that the relative variance of the weights could be large, right? So we'll need to bound that. Okay. Okay. So what should we choose as the reference distribution? I claim there's a very natural choice, which is this exponential of this negative f tap, and then with this quadratic term. Okay. So why is this a good choice? This is a good choice because if you write down the formula for the SL distribution at time t, right? So yt is this noisy observation, right? So this is a sum over the possible, like the sigma drawn from your Gibbs measure, and then what's the times the probability of seeing that observation y conditioned on sigma, right? So that's a Gaussian, and then if you put the linear part over, you will recover the partition function with this tilt y, which we said should be approximated by this exponential of the negative tap-free energy. Okay, so that's why we make this approximation. Okay, and then as another check, you can see that the score function of this, you take the gradient, it exactly gives you m hat, which is is what you are following in ASL. Okay, so this kind of makes a lot of sense. I also note that this it's very nice. Like this is very nice. It's something that's kind of this first part doesn't depend on time. This is well, so this is actually very related to like the nice linear tilt identity that Andre had.
So yeah. That approximation is exponential. The error in that approximation is exponential in n a priori.
Yes, but it's actually much better. It's in some sense like order 1, which is kind of it would.
Surely, can you show it?
For y's that are drawn from the SL process, we establish a certain kind of O of 1 closeness in the proof. Yes. Yeah. Okay, so here's our full algorithm. So we have ASL tapped, and then we have Jarzynski's equality gives you the ODE for the weights. Okay, you now have a rejection sampling ratio because you can go through the row T's. Okay, and then for this you need the partition function of the localized distribution, okay, which you can estimate because if we prove a functional equality for a localized distribution, we can sample from it. So we can also do simulated annealing to sample or to estimate this partition function. Okay, so we do. Okay, so we run this SL process. We do rejection sampling with this this importance ratio, part of it from the Jarzynski equality, and then we sample from this localized distribution. For this paper, we use this very particular Markov chain called the polarized walk, which is was more convenient to analyze. Okay. Okay. So what's the kind of proof plan? Okay. So I think I'll just kind of say in broad strokes. So there's kind of two parts to this. One is this error analysis for ASL to get this big O of 1 error in constant time. Okay, the two parts of this are this error of this covariance estimate. So this is where a lot of the spin glass theory and calculations comes in. With this like replica algebra, you can reduce, you do some calculations with overlap, some cavity interpolation. There are some additional regularity conditions you need, and then this is done with a lot of free probability. And then part 2, boosting to this order 1 TV distance, we analyze Jarzynski's equality with some path space analysis, and then we get the mixing for the local Markov chain. Okay, so this is tools from all over the place. So it was really a nice collaboration because everyone brought some different tools to the table, which were very very necessary. Okay.
Trying to understand the technology side. So
yeah.
Previously the bundle was W2 and boosted to KL. So which part of that is for that
So part one as KL, maybe I can answer this by, okay, so in this following slide, okay? So the first thing you want to, so first, it's easiest to get Wasserstein distance, okay? And how do you get Wasserstein distance with some Grandwalls inequality? Okay, so you have some ideal process, some approximate process, okay, that if your approximate process, the drift and diffusion terms are Lipschitz, okay, and you have a L2 error over the ideal process, then you can get this, if you do the synchronous coupling, you get this L2 error bound. Okay, if these are all constant, this is a constant. This bounds Wasserstein. Okay, our goal here is to get this O1 error for this mean estimate, which then by Gersonov's theorems gives you the KL divergence. Okay, and so for this, you basically, for the first part, you use this Wasserstein analysis, this Grandwall, between this ideal and this PhD tau process. I won't go through this, but basically we write down what are the desiderata that we need, and they're exactly, so you have this covariance estimate, and then you have the regularity and Lipschitz conditions you need so that you can apply that kind of Wasserstein bound, and then that gives you this. Okay. Yeah. Okay. Okay. So I'll for sake of I skip a lot, but so what's the hope for doing all these calculations is you look at there's very well, like the kind of static theory for this is very well established. So you can look at quantities like overlaps between like independent draws, and then you have very well, like there's good theory about like what the concentration for this is, and then you can do a lot of Gaussian integration by parts and other things to like reduce to these overlaps. It's kind of very long calculations, and you also need this additional technique of cavity interpolation, where you kind of decouple one of the spins, and then this leads to some additional cancellations that you need. Yeah.
What makes this covariance error easier than just directly the mean error?
Yes. So somehow, like if you look at the covariance, like the Q hat, it's actually kind of a nice expression. It's just like a rational function of these matrices. Okay. If you look at the M, it's actually nasty. It's like you have this tangent, so somehow it's just much easier I think, to deal with the Q hat directly. Yeah. I don't know. Okay, so let's skip everything here, and then okay. So Q, yeah. So this saying Q hat is this very nice structure. Is this structure of like this is called a resolvent. Okay, so you have this identity minus beta A plus D. Okay, and so since A is a random matrix, then we need to control these quantities. This is kind of where the free probability comes in. Okay, so you say like some sense that so free probability is like some kind of generalization, or not general, but like a version of kind of independence for these non-commuting random variables like matrices. Okay, and then you want to kind of understand how A and D, A interacts with diagonal matrices. This gives you that in this ideal setting, and then you want to kind of prove that it's kind of close to this ideal setting, and then this resolvent is very nice, and then you can do a bunch of complex analysis involving that, which collaborators pulled through. Yeah. Okay, so let's skip forward now, and then so the second part to kind of boost this was to get to understand these Jarzynski weights and then to get the mixing for the distribution, the localized distribution. Okay, so I'll just say one thing about this. So like, you can show these Jarzynski weights are very nice. Actually, they're sub-Gaussian. The idea is that they're Lipschitz in the appropriate sense. So you actually show their Lipschitz in the path space, so that like you think of that as a function of the Brownian motion path, and show its Lipschitz in the appropriate sense, which is this Cameron-Martin norm. And a Lipschitz function in Gaussian space is sub-Gaussian, and this is still true in infinite dimensions. Okay, so then we sample from the localized distribution. Basically, there's two parts to understanding this. One is for large constant time, you'll be very concentrated on a small wedge. Okay, this is just kind of like a posterior concentration. Okay, and then once we restrict to that wedge, we can have good mixing for this particular Markov chain. And then I'll also give a shout out to, so like a recent result by François Vader and Ahmed Roeder showed actually kind of had a, kind of goes beyond beta, goes 1/2 here. So like for any beta for large enough tilt, you can also get a 1/poly spectral gap. Okay, so I'll just say, well, what's the intuition here? The intuition is if you're concentrated on a small wedge, rather than depend on the operator norm of A, what you should really depend on is the operator norm of small, like, principal sub-matrices of A. Okay, and this can be a significant savings. Okay, and then you can formalize this with some like these kinds of decompositions for easing models. First into rank 1 and then product distributions. Okay, we can only get a factor of 1/2 because these results need the positive semi-definiteness. So you can kind of squash out the positive part but not the negative part. Okay, so that finishes part 1. So now the question is, can we simplify this algorithm? Okay, so that brings me to part 2. Okay, so we have this tension that stochastic localization can be these stronger results but need these strong conditions. Okay, so natural question is, can we show functional inequalities under weaker conditions than required in ASL, like naming those that suffice for ASL? Okay, and we think of this as like now like approximate stochastic localization because we actually don't need it as the algorithm. Okay, and this is especially useful for spin glass models where showing these conditions can be very challenging. Okay, so what's our notion of functional equality here? It's the weak Poincaré inequality, which is the usual Poincaré inequality, but you add this extra term here. And then what this says is that you only have mixing from a worm start. Okay, so you have this exponential convergence of this chi-squared divergence, but you have this extra term that's like, what is the worm start parameter you start with? So what's the L infinity of your divergence of your starting distribution? Okay, if you have a sufficiently strong weak Poincaré inequality, you can show that simulated annealing works. Okay, so the previous kind of strategy for that's in Bryce Huang's and their collaborators, is that if you have this measured decomposition, that you can get that from stochastic localization, but you're allowed to kind of have a small bad event, okay, that you just kind of throw away, okay, then you can get this weak Poincaré inequality. And you can kind of do early stopping for which, like, once, you know, if your localization process is doing badly, so it's not kind of conserving the variance, okay, then you stop that early. The problem is that there's this exponential, like this is exponential in kind of the covariance, okay, and you need high probability bounds on the covariance to make this work. So if you only have like second moment control, or like a finite moment, then you'll have this exponential dependence, which kind of trivializes the weak Poincaré inequality. Yes? So if you had a high power, you just get a power here, but you...
Yeah, but do they have a high power?
They actually get exponential, like, I think it's... Yeah, or like exponential some power, yeah, which is enough. Okay. Okay, so basically we show that in the, if you have, so these are kind of the outputs that we showed actually in the first paper, right? You have this mean estimate and Lifshitz drift and functional inequality for localized distribution. If you have this, then you automatically get a weak Poincaré inequality for your underlying measure. Okay, and this directly applies in our case. Okay. Okay, so this means that a much simpler algorithm works. Okay, so you can just obtain a worm start and then run Glauber dynamics from the worm start. Okay, and it turns out that actually the ASL distribution, so either the ASL distribution or this proxy rho t will give you a worm start. Okay, so this is actually a stronger thing we had to prove. It's stronger than just being okay for rejection sampling. Okay, so what's the kind of keystone for this proof is that there's this decomposition theorem for the weak Poincaré inequality. Okay, so if we can basically show that if we have this, look at the time t distribution, if this satisfies a weak Poincaré inequality for this proximal sampler for this, and then for most draws, you have the weak Poincaré inequality for the localized distribution, then you have a weak Poincaré inequality for your target distribution. Okay, this actually follows from a more general decomposition theorem for alternating Gibbs chain, noting that the proximal sampler is actually an alternating Gibbs chain. Okay. Okay, so this is, how much time do I have? No time. Okay, so okay, so what's? Let me see what I want to say. Okay, I'll just say very quickly what this proof is. Okay, so you. Okay, so the thing is we have this. So we have this KL divergence between the SL distribution and the approximate SL distribution. Okay, this and we can show that we have because the approximate SL distribution has Lifshitz drift. Okay, you can actually show an LSI for that. Okay, but the problem is that we want inequality for the true SL distribution, right? And if you only have this direction, then this could have like small mass, where p hat doesn't have small mass and kind of disconnect things. Okay. But the problem, the thing is, like somehow this shouldn't happen because this whole process should have been pretty regular. So if you just run time backwards, okay, you Gaussian smooth this, right? So it seems like this should no longer have this problem, and you can kind of formalize this with the conductance argument. Okay, and I'll note that this gives you the WPI for Langevin, and the getting it for the proximal sampler follows directly from this analysis of the proximal sampler, which is by Yongxin Chen, Sinho Chui, and others. Okay, so and then we also have kind of a similar argument with the worm star, which I'll skip. So let me conclude. Okay, so for this workshop, I showed theory and algorithms for diffusion models can really help solve challenging problems in sampling and statistical physics. I was really only thinking about Jarzynski's equality because I was kind of exposed to all these recent works on it in kind of the sampling and machine learning literature. And I hope maybe some deep dive into sampling for these model problems can also inform their design. And I think it's kind of really remarkable that you have these continuous and algorithmic tools. You can prove some purely discrete and non-algorithmic results, right? So the end result we had for the weak Poincaré inequality actually kind of required all the machinery, even if for like Jarzynski and ASL, even if you're not actually running those algorithms. The main open problem, which we are working on, is trying to extend this all the way up to beta. And then we'll actually be working on some blog posts describing this, so which we'll put on Juspreet's blog. So look out for that. Okay, thank you. Yeah.
So yeah, I may miss some of the discussion that you have. So I mean, you're comparing the rejection sampling with Jarzynski.
Yeah.
But Jarzynski is kind of just like a rejection sampling on pass space, right? So is it the difference like whether you just do rejection endpoint or the path space?
Yeah, so I kind of glossed over this. It is fine. So like the actual, where is it? Yeah, so this actual Radon-Nikodym derivative is actually this conditional expectation over the endpoint. Okay, but if it's like if this WT is already really well behaved over path space, then kind of can only get better if you condition. Like the variance can sort of only go down. Yeah. Yes.
So if I read your results right, to get epsilon error, you had an exponential dependence on
Yeah.
epsilon. Do you think that's necessary?
I don't think it's necessary, but like proving it requires proving more things about spin glasses because like we basically only show like some like second moment bound, and like to get better you need like better control over these like error quantities.
If not, we can now break for lunch. Thanks for the wonderful.
Jeff and Davis, introduction to